happening at deeper depths in the plumbing systems, and what's causing upwelling or downwelling in these systems. And then further on from there, my work is looking at how this changes during lava flow propagation, what causes lava flows to propagate and what causes them to stall, and then what are the thermal implications to outbreaks or breakouts occurring in these systems. And then finally, I'm going to show you how, by better understanding the thermodynamics of these systems, we can input some of that data into lava flow propagation models. And I'm going to use an example of the Fissure 8 lava flow emplacement from Kilauea in 2018 to show you, some improvements that we can potentially make by better understanding these systems thermally. So traditionally and still regularly, we take thermal measurements of lava flows discretely using thermocouples. But obviously the problem here is we're only getting very small snapshots of the entire lava flow system. We're not understanding the entire system. We just got small points. And so a lot of my work has been using various different sensors, from the satellite to airborne sensors like this old spy airplane. And also I've been developing some ground-based instruments to better understanding what's happening dynamically at very high temporal and spatial resolutions, but also trying to get some sort of spectroscopic understanding of those things in the field as well. And so that's kind of motivated most of my work in developing new instruments in a very kind of cheap, a very cheap and lightweight way, to better understand how the cooling and dynamics occur and help us forecast those. And so to do this, I took a pretty standard FLIR camera and put it behind and put a filter wheel in front of it, shown here with 6 bands, very distinct wavelength regions, to understand how the energy emitted from that surface is changing at different wavelengths. Through this process, there was a few complications in the instrument as a result of temperature drift as this sensor is heating up, and also we have some transmission issues with energy passing through the filters and then going through a lens and then hitting the sensor. And so I've done a fairly robust calibration for this. I'm not going to necessarily share that with you today. But what I am going to share with you is some of the validation that I did to prove that the data I'm collecting is accurate and reliable. And so to do this, I went to the Syracuse Lava Flow Project up in upstate New York. I'm sure many of you have either heard of this setup or have been there themselves. But essentially, they pour molten degassed basalt over a sand substrate. And what I did is I set up the camera, which I'm going to from now on call the MMT cam, of this during its entire propagation, and then I set up radiometer and thermocouples to validate the measurements that I was acquiring from the camera. And I saw a good match between the two data sets that I used, and I see I observed various changes as the flow propagated and cooled and formed this glassy crust. And then I also, looking at the data more spectroscopically, here we see a change in the absorption of the material as we decrease and cool those lava surfaces. And we see kind of a narrowing of the absorption and a shallowing. And this is in a fairly non-linear relationship. And so a lot of my work has been trying and quantify this relationship with temperature. So taking a step back, briefly going over infrared spectroscopy. As most of you probably are aware, all matter and materials emit radiation continuously over all wavelengths. And this has been modeled in the early 1900s by Max Planck for perfect emitters. And he managed to model how the energy emitted from that surface changes with wavelength and with temperature. But obviously these are for surfaces that are perfect emitting, but in reality, this this isn't true for nature, and so there is some variability in these curves, and this is where we can see some spectroscopic information. The majority of my work is concentrated in the thermal infrared region of the electromagnetic spectrum between 8 and 12 microns. The reason for this is that there is an atmospheric window here, so there are less complications due to atmospheric water vapor and CO2, and so the corrections are a lot more simpler for that. And also there's a strong SiO stretching band region, and also aluminum hydroxide deformation region that occurs, so we can get more diagnostic information of what's of various composition changes within this region of various surfaces that I wanted to look at. And so obviously, as I alluded to a second ago, all materials aren't perfect emitters, and so they are selective at different wavelengths. And so to be able to easily compare different surfaces, different temperatures, different compositions, what we can do is we can normalize it by taking our measured energy, or radiance in this instance, of that surface, and dividing that by that same surface if it was a perfect emitter at the same temperature, using Planck's equation. And so once we do that, we get this unitless number called emissivity here. And so this enables us to, it's kind of similar to a reflectance or transmission in that regards. Those of you who used various different spectroscopic techniques, but we can better compare different materials more readily and more easily. And so one of the first things I did was try and determine, well, what's the point in doing this research if it's not going to make any difference to the volcanology community? So I did some calculations where I saw what the impact of changing emissivity would have on the energy that's emitted from that surface. And so I took some numbers from the literature, and I modeled this here. And as you can see, by changing emissivity, we can reduce the amount of energy that's emitted by that surface across various temperatures by up to 16%. And then what does this mean for potentially lava flow modeling, which is one thing that we all want to care about? Is some previous work has been able to quantify this using a thermoradiological lava flow propagation model, and seen that by taking into account a low emissivity value of a molten portion of the flow, we actually reduce the heat flux, reduce the cooling rate, and as a result, we model longer flow runout distances. So the majority of the work I've been doing, or was doing during my PhD, was at Kilauea Volcano. Most of the time I was looking at the pre-2018 eruption. So I'll show you data from the lava lake at Halemaumau, which is here, for those of you who don't know. Also looking at various Pahoehoe lava flows on the coastal plain that propagated from the Pu'u lava lake, from the Pu'u event. And then I'll also show you some data later on from the 2018 Lower East Rift Zone eruption, which I'm sure you've all seen various pictures and images from, so I'm not going to dwell on this too long, but I have some data from there that I'll show. So I've talked to you about the two main thermal properties that I'm interested in, temperature and emissivity, but I also wanted to look at these kind of higher level derived properties, heat flux and fraction of exposed melt. Fraction of exposed melt is kind of a proxy calculation that I've used, where I've taken the temperature of a pixel within a surface. I've taken that from an ambient temperature off to a leve of the lava. I've divided that by then the liquidus temperature for the composition of the basalt that I'm looking at, and took that again away from the ambient temperature. And so this property is kind of a proxy of how much of the material is above the liquidus, and so how much of that material within that pixel is completely molten. And then secondly, I'm looking at heat flux, and I'm using three components in the heat flux calculations. First, it'd be the radiative loss as a result, and this is in a relationship with emissivity and temperature to the power 4. I'm using force convective flux, and this is in relationship with temperature here, and that's because during most of the data that I acquired, there was some wind, and then finally I also calculate conductive heat loss, again with respect to temperature and various thermal properties of a basalt. I'm ignoring heat flux due to rain in this instance because there was no rain when I was acquiring data. So here's just a couple of the examples, some of the data that I'm going to show you in the next couple of minutes. So first of all, there's some Pahoehoe lava lobes propagating down the coastal plain. Here is the same kind of scene, but in the thermal infrared. And I'm just showing you the region of interest that I'll be showing you data from in a few minutes. Second of all, here's the lava lake at Halemaumau. And then down here is again another region of interest that I'm going to be using. And again, this is another scene from the coastal plain with some small breakouts occurring, and then the same scene in the thermal infrared. So moving on to some of my results. I first wanted to get a better understanding of how these thermal properties correlate or decorrelate with each other over a fairly stable hot target. And so for this, I used the lava lake at Halemaumau. And in this schematic, I have temperature in the leftmost column. Next to that is emissivity, fraction of melt, and then our heat flux. And then I'm just showing you 3 different time steps through this one data set that I have. And as you would expect, we have the highest temperatures at the margins of these plates and the coolest temperatures in the center of these plates where we have the most crystallization occurring. But we do see some gradation between the two in this data. In emissivity space, we actually see the opposite correlation. We actually see lower emissivity values in these marginal regions. And then looking at the fraction of melt is exactly what we'd expect, correlates directly with temperature, as does heat flux. However, as a result of the relationship between temperature, emissivity, and heat flux, we can also pick out this kind of more broader high heat flux region towards the top of the lava lake in this image, in this data set, and a fairly low heat flux towards the bottom. And this can imply some sort of uplift maybe, and some downwelling as well. And this is also shown in the video data of the crust movements across this plate as well. So we can get some understanding of maybe what's going on within the plumbing system of that conduit here. And so looking at these thermal properties in temporal space, I am just plotting the frequency of the data with respect to the various thermal properties and respect to time. So going from purple all the way to yellow, and over this 15 or so minute time period, we don't see too much fluctuation in the thermal properties of the lava lake. However, we do see a fairly strong bimodal distribution, and this is likely a result of the fact that we have two very distinct features within the lava lake. We have the crustal plates and then the hotter molten margins, and so they're picked out in these frequency graphs. But overall, it's a fairly stable system, which implies that there's probably some sort of equilibrium between the inputs and the outputs during this period of time. Obviously, people have shown that there are lots of long-term and short-term trends here, but just in this data that I'm showing, that there's not much variability. And so finally, I wanted to put all this data into frequency space by running a 2D and a 1D fast Fourier transform of that data. And this is to understand directionality and the frequency at which we see variability occur and to what magnitude this happens. This has been done quite a lot by people that have looked at drainage basins and DEMs and topography, and I'm just applying the same technique. Instead of looking at height, for example, I'm looking at various thermal properties. So, for example, this is just an ideal surface, and I'm just going to show you how that plots onto the graphs that I'm going to show you again in a second. So, for example, in the y direction, we have this high frequency variability, but with low amplitude. And so in this frequency space graph, that plots again in the y frequency at high values, but it has a low amplitude. So down here. And then in the x direction, we see this low frequency, high amplitude variation. So here is plotted with these high concentric rings close to the origin in the x frequency direction. And so I've done the same, but for these various thermal properties that I'm interested in. And the reason for doing this is to get away from the sampling bias of having, say, a transect through the lava lake, and you can only put maybe 4 or 5 and you plot them up. Whereas here, there's no real sampling bias or analysis bias. And so we can understand I can talk about the directionality of the frequency of which changes occur in these properties within the lava lake. So, for example, if we look at the temperature, if we look at the variability in temperature space, we can see that very close to the origin, we have these very low frequency changes at very high amplitudes in a kind of a north-south direction. And so if we go back to our data, we can see that, in this direction, we do have this change over fairly large distances of about 100 meters. And that's what's shown in our data sets here. But we can also see that there's also this high frequency, low amplitude change within the lava lake, which isn't very apparent just by looking at the data. And so this can kind of maybe talk to some smaller scale variations that aren't very apparent when looking at a whole system. And then finally, what I did was I looked at this data in temporal space to see, how do these does the frequency at which these changes in thermal properties occur, does that vary over time? And what the data kind of shows is fairly boring, is that these actually happen over very long time periods, but with some kind of spread to more short-term periods of time, but it's mostly dominated over long periods of time in this instance anyway. So the next thing I wanted to do was to then take from what I understood from a lava lake and apply that to a lava flow, or a small lava flow at that. And so this is some results from a Ho'i lava flow on the coastal plain. Again, the same type of figure I'm showing here, but instead of only looking at 12 minutes, I'm looking at 81 minutes. Something interesting to look at here, 81 minutes, we see this large breakout at very high temperatures, and this correlates with fairly surprisingly low emissivity values from what we would have normally accounted for. Obviously high fraction of melt, but our heat flux is significantly lower than what we'd have normally expected. And this is a consequence of having lower emissivity in this area. And so this is saying that we are not actually losing heat very efficiently compared to other regions of this lava flow, or this lava flow field. Another interesting thing to note is in the back of this data, we can actually see this high flux region, and this is likely implying the supply of lava to the active front. So again, looking at that data in temporal space, we see a pretty large dramatic change over the kind of 81 minutes, and that's a result of that large large breakout that occurred. And what we can also see is this is kind of multimodal distribution. It's not very bimodal. There's many components that are contributing to the results that we're seeing, and this is likely a result of the complex interplay cooling that's happening as we're going from a molten to a viscoelastic crust, to a glassy crust, to a more crusted, to a more cooler crusted surface, and this just implies the complexity that there are within these systems, and to try and quantify them to understand how propagation works is something that we need to try and do a better job of. And again, I'm going to show you this plot. In the one interesting thing that these can show in lava flow data sets is that this can give us some sort of understanding of directionality. This can show us, in which orientation are these breakouts predominantly occurring. So this can potentially imply, is a breakout going to happen along the flow in X direction or in Y direction? And so here we see, again, a very north-south orientation of the highest amplitude variations. Again, that's very similar in all these data sets. There's also a more northeast-southwest orientation. And this is likely a result of that large breakout occurring right at the bottom of the data set towards the end of the acquisition period. And then I've just taken again a few 1D temporal distributions at these distinct points within the 2D frequency space. And again, these processes occur over fairly long periods of time, obviously with respect to the amount of time I was looking at it. So these are happening over minute timescales rather than second timescales. But there is a fairly decent spread, and we do see faster processes changing and occurring within the system, and that's likely a result of the small breakouts that are occurring off to the side, but they're not really traveling very far, or and they're very short-lived events. So the next thing I wanted to do was to understand how these thermal properties varied along flow within a channel from initiation at the vent to termination. And so to do this, I was lucky enough to find a small tumulus-fed lava flow that was about 6 meters long, and I was able to quantify this. And I wanted to use this to better understand the relationship of these during propagation. And again, this was taken pre-May 2018 on the lava flow field from Pu'o. And so here I'm just showing you this transect from vent to flow termination, just over 6 meters long. Again, when we see breakouts, we see high thermal outputs, which have an inverse correlation with emissivity, and then but that's not directly or linearly correlated to our heat flux. And generally, over this period of time, we see a general decrease in the thermal outputs and a transition to further points down flow, obviously as the flow is propagating, as you would expect. And so from here, I got a better understanding of what thermally is going on within a flow. And then the next thing I wanted to do was see, well, okay, can I use this data to improve lava flow propagation models? And so to do this, I wanted to understand the relationship between temperature and emissivity, and how emissivity then affects heat flux later on. And so what I did is, using that same tumulus-fed lava flow data set, I used the region of interest to plot emissivity at the various wavelengths collected by the MMT-CAM for different temperatures. And as a result of the sampling bias, obviously there are more surfaces that are cooler and less surfaces that are hotter molten temperatures. I worked out the 2 sigma variance of that data, and then calculated my quadratic and linear relationship models from that variance. And what it shows is there is a general inverse trend between emissivity and temperature at all wavelengths, with some less distinct than others, and there's also a positive relationship at certain wavelengths. So, for example, here at 11.35, and generally a linear relationship matches the data more strongly than a quadratic fit. And then what I realized I needed to do was actually combine this spectral information into kind of an average emissivity value to enable it to be more simply and easily combined with previous studies, and also integrate into flow propagation models. And so again, I still do see this inverse trend when we look at the general relationship between emissivity and temperature in the thermal infrared region across the typical liquidus temperatures of a Hawaiian basalt. And so I had to choose a flow propagation model with which to test and integrate this relationship with, to see how it would affect model results. And I chose PyFlogo as its a thermorheological model that has strong control, is controlled by cooling, and it's very robust when it comes to calculating the thermal and the rheological regimes of the flow during propagation. And as well, it's also designed for channelized flows, and I'm looking at channelized flow, or my hope was to look at the channelized flow from Fisher 8 in 2018. And additionally, it was recently updated for Python, which enabled the easy integration of different modules for calculating different parameters. For example, you can put in your own calculation for viscosity or cooling rate or crustal formation or crystallization. And so that enabled the easy adaptation of what I wanted to do, which was change the radiative heat flux model within this within the entire model. And so I first of all wanted to validate the model that I made to input into PyFlogo, and to do this, I used the same data set of the Tumulus lava flow to do this. And I compared results of varying emissivity with temperature or surface temperature of the flow with the results from the original model using a constant emissivity. So here, in the next few plots, I'm going to show you various plots with run-out distance and various thermorheological parameters. And the dashed blue will be the original model, and then the black line will be the change that I've made. And this red vertical line shows you the final run-out distance of the flow derived from ground-based measurements. And so here I'm showing you results with channel width, with channel width and heat flux, as well as some ground validation measurements. And generally, by using the variable emissivity model, we do have a stronger agreement with the ground measurements, and we also see that the flow does propagate further by up to about 5%, and that's a result of this heat flux calculation being lower than expected as a result of us calculating lower emissivities for the surface. And so once I'd done that and I'd kind of refined the model for the new parameter, I then wanted to do a full-on test with a more typical lava flow that we'd want to model. And so here is just some of the data sets I'm used to validate these results from the Fisher 8 lava flow during 2018. So here's from the vent. This is the perched lava flow, and then here's the more distal regions of the flow where it's more channel confined. And then here is a thermal map produced by USGS, and I've overlain in red here the central channel that I'm trying to model in these results. And so here is the results with respect to emissivity. Again, we see this strong this fairly strong variability in emissivity with respect with run-out distance, and this changes more dramatically at further run-out distances, typically within the last 20% of the flow. This is likely a result of the fact that we see the greatest amount of cooling, crystallization occurring here, again, in this region. And so here are some more results with channel width. This was the main parameter I used for validating this model. As you can see, there's a strong agreement between the ground-based and the model results, especially in the last 20% of the flow. And again, the model causes the run-out distance to increase by about 830 meters, which is a significant amount when determining hazard zones and trying to understand, how far these flows may propagate. The one downfall of PyFlogo is that it didn't well constrain the very kind of wide perched channel that occurred close to the vent here. However, it was still able to do a good job at matching the results in the more distal regions of this flow. And again, this is likely a result, the run-out distance increasing is likely a result of our temperature staying higher for longer as a result of cooling rates being reduced as we're losing less radiative heat flux. And finally, I'm just going to show you how some of the rheological properties are influenced by this variable emissivity. For example, crustal fraction and formation is lower as a result. This causes viscosity to also stay lower for longer periods of time, and as a result, our velocities are much higher, or are higher as well. And this is mostly this divergence is mostly seen towards the more for the final regions of these flows. And that's where our greatest influence is observed. Okay, and so with that, I'll just conclude. Thermal properties do vary pretty non-uniformly downflow, and they vary very extensively, both in spatial and temporal space. I've shown there is an inverse relationship between temperature and emissivity, which is not necessarily expected, and this has a strong influence on our heat flux calculations. It's not uniform at all wavelengths, but generally this is the trend that's seen. By accounting for this variability with temperature, we can increase our run-out distances of lava flows by about 7%. In my example, that's 800 meters. That's a good amount. And this is a result of reducing that heat flux, and the divergence in these model outputs is seen the greatest at the more distal regions. So thank you for your attention, and I will answer any questions you guys have.
Excellent. Thanks so much, James. This is excellent. We do have time for questions and discussion. So please feel free to type some things in the chat or raise your hand in that raise a hand function, and you can just ask your question. And while we'll get folks doing that, James, I wondered if you could comment a little bit. I think this is extremely exciting to be able to do kind of a total heat budget of some of these flows.
Yeah.
And I wonder if you could comment maybe a little bit on some of the technical challenges of getting in the field, getting the resolution and kind of coverage that you need. Let's say you wanted to try to do a total heat budget.
Some of the challenges, there are many challenges.
Yeah.
So the many challenges come from, there's always a trade-off between the spatial extent you're able to look at in the entire flow, the spatial resolution of your data in itself, and the time at which you're able to take those measurements over, and also the resolution of that spectral information. And there's a trade-off that has to happen between them all. For example, if we look at a satellite data, we have great extent resolution. We can see the entire flow all in one image, but we can only look at, say, our pixel size is 90 meters. So we miss some of these more complex interactions in these flows, which I think play a significant role in flow run-out distances and models. But then looking at the ground, I'm doing a little bit better than just poking it with a thermocouple, even though there's still great use in doing that. But I can't see the vent and the flow front at the same time. And then there's also this trade-off where, you know, you can take a piece of basalt and put it in your spectrometer, and you can look at it at 2 wave number increments, whereas I can only see what's happening spectroscopically at, you know, at like 6 points between 8 and 12 microns. So you know, in an ideal world, you know, the best thing to be able to do would be to maybe even, you know, start to miniaturize these even more, and maybe put them on drones or put them on helicopters or something like that. You know, that's one way, but I think the goal for us is to try and keep this as cheap and as reliable as possible, but making sure that still our data is accurate and precise, and we can you know, we can trust the data, you know, in the same extent, you know, and that's a goal in it. That's a struggle in itself. Sure.
Oh, thank you. Colin has a question. Looks like Colin.
Hey, James.
Hi, Colin.
Super cool talk. It's really awesome to see somebody doing some real efforts at quantitative work and thermal imagery. So thanks for that. I had 2 quick questions. One, is the north-south stretching in your periodograms, is that at all related to foreshortening in the images, or are you accounting for your viewing angle?
That's a great question. No, that is not a result. I have taken into account the different pixel resolution as a result of not looking at it directly above. So yes. Okay,
great. And then I was just wondering if you were able to capture any variations in emissivity and other thermal properties in the lava fountains that you imaged.
Unfortunately, I think there are. I haven't spent a lot of time looking at them. It's a really cool data set that I haven't spent a lot of time looking at, unfortunately, just because of, you know, wrapping up PhDs and stuff. And but it would be really interesting to look at and spend some time for sure.
Okay. Is it when you're flipping between different spectral bands, is there like a time lag? Like, well, how fast are you able to switch between those?
Okay, so I can switch between them within 0.8 of a second. So there is a small time lag. And that's a trade-off that I also have to make, but I think that's a fairly, you know, reasonable assumption that I can make there, that they're within a certain amount, yes.
Okay, cool, thank you.
No worries.
Jensu has a question on chat, and her question is, how do the temperature oscillations? Sorry, I'm misreading. How do the temperature oscillation wavelengths compare between lava flows and lava lakes? And also, have you looked at the Pohohoi to transition using your tools?
Good question. I would say the variability in the lava lakes happen at lower frequencies than we see on lava flows. I think lava flows, we see variations happen over smaller distances compared to the lava lakes. I think that was I'm a bit confused by that question, but I think that's what you were asking. And then the transition between RR and Pohohoi, no, I have not looked at it because I wasn't able to see that transition in the field. I wasn't able to get to any I haven't been able to get to any flows that have done that, but that would definitely be something interesting and worth looking at if someone hasn't already done it.
And Jensu, feel free to just jump in if there are any follow-ons for that.
Yeah, James, sorry, there's a lot of background noise from the ventilation, so I didn't want to say it out loud, but this is very cool work. I'm really excited to see how we'll be able to integrate it into some of the flow models and lava lake models that we have out there.
Yeah, definitely. I think it's important for sure. Thank you.
Other questions, discussion points?
I mean, I'll definitely keep quizzing James if nobody else wants to jump in, but I don't.
Go for it, Colin. Yeah.
Go for it, Colin.
Yeah. So I was kind of curious. I mean, I was actually thinking along the same lines as Junsu there about whether or not you know anything about that emissivity variation with temperature and how much it might be related to things like glass content and crystal content, and if there's any sort of experimental validation of that, or if you have some intuition from the data.
Yes, I can postulate. I don't have any validation to say that for sure. I think there is some evidence in some of the data I've seen that the linear trend that I'm showing is an oversimplification. And I think as we get into glass transition, there are some more complex changes that occur. And I think the best way of doing that or looking at that will be through experimental petrology in the lab, just because of the spectral resolution that we can get. And then I think the importance there will be scaling that for models, which, you know, I'm sure many people are thinking about. And I think that's definitely somewhere that we should go into. And to a certain extent, we do see it in the field. I have seen it in the field, but it's just the spectral resolution isn't quite there to prove it yet, I don't think.
Looks like we have a question from Alan Lerner. Does absorption by gas emissions interfere with quantitative IR measurements?
Yes, it does. And I had to do some corrections for that at the lava lake as a result of the strong degassing that we saw. But I essentially just used a gas cylinder model to calculate the transmission and the absorption likely from an SO2 and CO2 plume from there as a relationship to some ground measurements that we took we took some gas measurements while we were there, and then I modeled that through the data to correct for it. It isn't perfect, but it does a good job. On the lava flows, it's less of annoyance. There's not too much interference from gas in that instance.
I guess I have a somewhat related question. Do you need to worry about the kind of scale of roughness? Is this something that is of concern?
Yes, I think yes, it is. How to precisely deal with that is not straightforward, I guess. I'm mostly ignoring it in the data sets I'm doing, and that's just because the temperatures that we're looking at are going to be this is the strongest signal that we're looking at, and not roughness necessarily. I think for colder surfaces, 100% it needs to be taken into account, and there has been some work done on that previously, and yeah.
Thanks. Other questions, discussion points? Well, thanks again, James. This is excellent, and it was great blend of technology and interpretation of data, and going from benchmarking to field applications. That was really great. Everyone, please let's thank James again. What we can do if James has a few minutes is, if you want to stay on the line for a couple questions. There are always a few little last questions, and we can just take it in a smaller group. But please join us again next week.
Thank you, everyone.
Great job, James.
Thank you.